Hi everyone, welcome back to Coding Fab. In today's video, we're going to take on an exciting machine learning task, handwritten digit classification. This project is all about teaching a computer to recognize handwritten numbers using image data. We'll walk through how to load and visualize the dataset, build a convolutional neural network using TensorFlow, train the model, and evaluate its accuracy. If this is your first time working with image data or neural networks, don't worry. I'll guide you step by step and explain everything in a clear, beginner-friendly way. You'll see how these techniques apply to real-world tasks and build your confidence in working with deep learning. All right, let's get started. 1. Understanding the project. This project falls under the classification category of supervised learning, where the goal is to classify handwritten digits 0 to 9 based on pixel values in small grayscale images. The dataset comes from scikit-learn's built-in digit recognition dataset, which contains 8 by 8 pixel images of handwritten digits. Each image represents a number from 0 to 9 and is labeled accordingly. The data type here is image-based, as each input is a matrix of pixel values. Also, the pixel values range from 0 to 16. You can check the details about this dataset on sklearn's website like this. This task is framed as a multi-class classification task because there are 10 possible digit classes, 0 through 9. To solve this problem, we use convolutional neural networks, which are well suited for image recognition tasks. CNNs can automatically learn spatial hierarchies of features and patterns within the image, making them ideal for recognizing digits from raw pixel inputs. The performance of the model is evaluated using several metrics. Accuracy shows the overall correctness of predictions. Precision, recall, and F1 score give more detailed insight into how well the model performs on each digit class. A confusion matrix is also used to visually understand which digits are being confused with others. The project is implemented in Jupyter Notebook using tools such as TensorFlow and Keras for building and training the CNN, and Matplotlib for visualizing samples and performance results. Also, we will follow the basic machine learning workflow shown in the upper right. Okay, let's get started. 2. Loading the data. The goal is to import the dataset, which contains images of handwritten digits and their corresponding labels, 0 to 9. First, import load digits from the sklearn datasets. Next, load the digits dataset into a variable called digits. It contains both the image data as flattened arrays and the corresponding labels that are the correct digits. Then extract the features and target labels separately. Three, exploring the data. The goal is to understand the shape, structure, and variety of the images and labels in the dataset. Let's visualize sample images. This example is visualizing the first 5-digit images. It creates a new figure. It's like a canvas to draw on, with a custom size of 10 units wide and 2 units tall. This ensures the images are displayed clearly in a horizontal row. Next, loops through the first 5 images in the dataset, indices 0 to 4. Then create a subplot inside the figure. That part means 1 row, 5 columns, and I+1 subplot. This lets you display 5 images side by side in a single row. The image show displays the IT image using grayscale color, black to white. Image's I is an 8 by 8 matrix of pixel brightness values. Also add a small title above each image showing its true label. Axis off hides the axis ticks and grid lines to make the images look cleaner. Finally displays the complete plot with the 5-digit images and their labels. Now you'll see 5 handwritten digit images in a row, each labeled with the digit it represents. This helps you visually confirm that the dataset is correctly loaded and labeled. 4. Preprocessing. The goal is to prepare the image data for a convolutional neural network. It expects the input image shape to have a specific 3D shape, number of images, height and width of each image, and number of channels. And the label shape needs to be one-hot encoded. Also, CNN expects the normalized pixel values to help the model learn faster and more accurately. We scale them to a 0 to 1 range. Let's reshape the input first. -1 means figure out the number of samples automatically. 28 means the height and width of each image. The last one means the number of channels. It's 1 because this is grayscale. Next, reshape labels. Convert the digit labels into a format that a CNN can understand for classification, called one-hot encoding. First, import the toCategorical function from TensorFlow Keras. It's used to convert class labels into one-hot encoded vectors, so the result is that each label is transformed from a single number to a vector like this. For the input x, normalize it divide by 16 because the pixel values range from 0 to 16, according to the sklearn website. Then split the data. This step is the same as the other tasks. Five, training model. The goal is to build a CNN that can learn patterns from image pixels and correctly classify digits, 0 to 9. First, import the required modules. Sequential is a linear stack of layers. Conv2D is a convolutional layer that detects features in images. Max pooling 2D reduces image size to make learning faster and reduce overfitting. Flatten turns 2D image data into 1D before passing to dense layers. Dense is fully connected layers, like traditional neural networks. Next, build the CNN model. This means the first layer is 16 filters, 3 by 3 kernel size. ReLU activation introduces nonlinearity. The input shape tells the model that the input is an 8 by 8 grayscale image. Max pooling reduces each 2 by 2 block to its max value, then downsamples the image by half. The flatten method flattens the 2D feature maps into a 1D vector to connect to the dense layer. The first dense method creates a fully connected hidden layer with 64 units and ReLU activation. The last dense method outputs a layer with 10 units, one for each digit, 0 to 9. The softmax activation turns outputs into probabilities that sum to 1. Next, compile the model. Optimizer Atom automatically adjusts learning rate. Loss categorical cross-entropy is used for multi-class classification with one-hot encoded labels. Metrics accuracy tracks classification accuracy during training. Finally, train the model. Trains the model for 20 epochs and uses 32 samples per batch. This means the model will go through the entire training dataset 20 times. Each full pass is called an epoch. More epochs can help the model learn better, but too many might lead to overfitting, where it memorizes the data instead of learning patterns. The batch size 32 inches means the model will look at 32 samples at a time before updating its internal weights. The training data is divided into small chunks of 32. A smaller batch size uses less memory but might be slower. A larger batch size can be faster but may not generalize well. So common sizes are 32, 64, and 128. And 20% of the training data is held out for validation to monitor how well the model generalizes during training. History stores training and validation accuracy and loss over time. 6. Prediction. The goal is to use the trained model to predict which digit appears in each image from the test set. Okay, let's predict classes on the test set. This will give you an array of probabilities for each digit. For example, let's check the probabilities for a specific image. The image and each prediction for that image look like this. It says the model is confident it's a 6. But this shows all the probabilities for one image, so it's a little hard to understand. So let's change it to only return the class label with the highest probability. To convert probabilities to class labels, we can use argmax method to find the index of the highest probability in each prediction. Okay, let's print out predicted labels and true labels. Now you have actual class predictions. As we checked, the predicted first class label is 6, and it matches the real class labels. The other predictions also seem to match the actual class labels. Next, let's evaluate the model. 7. Evaluation. The goal is to build a CNN that can learn patterns from image pixels and correctly classify digits, 0 to 9. Okay, let's create a classification report that shows detailed metrics. It includes accuracy, precision, recall, and F1 score. Accuracy is an overall percent of correct predictions. Precision tells how many predicted digits were correct. Recall tells how many actual digits were correctly identified. F1 score balances between precision and recall. In addition, support is the number of samples in the test set for each class. Macro average means that the unweighted average across all classes. So each class is treated equally even if it's rare. Weighted average means that the average weighted by support. So it's more realistic for imbalanced datasets. Common classes have more influence. All right, let's have a look at the result briefly. The model achieved an overall accuracy of 96% on the test set, which means it's correctly predicting 96 out of every 100 digits. Most digit classes like 0, 2, 3, 4, 5, 6, and 7 were predicted perfectly or nearly perfectly with F1 scores close to 1, meaning both precision and recall were very high. Digit 1 had a slightly lower precision, 0.84, but high recall, 0.93, meaning the model often correctly identifies ones, but sometimes mistakenly labels other digits as 1. Digit 8 had the weakest performance, with a recall of 0.77 indicating that the model missed some true 8s, though precision was still perfect at 1.00. The macro average and weighted average are both 0.95 to 0.96, confirming consistent and strong performance across all digit classes. Next, let's check the details with the confusion matrix. It shows exactly where the model got confused between digits. For example, digit 8 is the weakest, often confused with 1 and 9, which may look visually similar in 8 by 8 pixels. You could improve the recognition of 8 by adding more training data for 8, using a deeper CNN or data augmentation, and examining pixel patterns where misclassifications occur. Overall, the model is highly accurate with only minor confusion between digits. 8. Visualization. The goal is to display some test images alongside the model's predicted labels and the true labels, so you can spot correct and incorrect predictions visually. Let's plot 10 test images with predictions. First, creates a new figure or canvas to plot the images. Figure size sets the width to 12 and the height to 4 in inches. Next, loops through the first 10 images in the test set. Each loop will create one subplot for one image. It divides the figure into a 2-row 5-column grid. I+1 places each image in its respective subplot position, since subplot index starts from 1. The image show displays the test image using grayscale color. The reshape converts the 1D input back to its 8x8 pixel format. CMAP makes the image black and white. Then add a title above each image, including the true label and the predicted label from the model. The axis off hides axis ticks and labels to keep the view clean and focused on the image. Then adds a main title, adjusts the layout, and displays the result. Now you can see the 2x5 grid of images. Each image shows what digit it is and what the model guessed. Looks like the model predicts all the numbers perfectly in this sample. Okay, that's it for this project. Overall, the model achieved an accuracy of 96% on the test set. Most digit classes were predicted perfectly or nearly perfectly with F1 scores close to 1, meaning both precision and recall were very high. However, we did notice some areas for improvement. Digit 1 had slightly lower precision, meaning the model sometimes mislabeled other digits as 1, even though it was usually good at detecting actual 1. Digit 8 had the weakest performance with a recall of 0.77, indicating that the model missed some true 8, though precision was still perfect at 1. For further improvement, we can think of several ideas, such as adding more training data and using data augmentation techniques. Also, we can try a deeper CNN and examine pixel patterns where misclassifications occur. And that's it for today's lesson on this topic. We explored how to classify handwritten digits using image data and a convolutional neural network. You learned how to load the dataset, prepare and visualize the data, build the model, train it, and evaluate its performance. Along the way, we also discussed what makes CNNs effective for image recognition tasks and how to interpret the results. Projects like this are a great way to build real-world skills while getting hands-on experience with deep learning. Whether you're preparing for a job in AI or just starting your machine learning journey, tackling image classification helps solidify your understanding of how neural networks work. Keep experimenting, adjust your model, try new architectures, and watch how small changes can lead to big improvements. Every project you complete brings you one step closer to becoming confident with machine learning. Okay, thanks for watching today's lesson on coding Fab. I hope you found these tips useful and feel more confident. Remember, practice makes perfect, so try using these tips in your project. If you enjoyed this video, don't forget to give it a thumbs up, share it with your friends, and subscribe for more Fab coding lessons. Until next time, keep practicing and stay Fab.